Hello, my name is Joachim Haensel. I'm going to present on the topic of collective risk minimization via a Bayesian model for statistical software testing. This work was done in cooperation with my colleagues Adriano, Johannes Dyck and Holger Giese from the System Analysis and Modeling Group at the Hasso-Plattner Institute in Potsdam. Let us first have a look at some trends in recent years in the autonomous vehicle industry. The data we'll see is provided by the Department of Motor Vehicles of the state of California. The chart on the left-hand side shows the increasing number of companies that test autonomous vehicles under real-life conditions. The chart on the right-hand side reports on the number of accidents where these kinds of vehicles have been involved. In presence of this exponential growth of accidents, we identified a need to work on the reliability of these systems, which translates to risk considerations in the context of safety-critical systems. More specifically, we need to ensure an upper bound in risk, even if these systems are challenged by the uncertainty of the environment in which they will operate. So what are the factors that lead to these accidents? With human driver-driven cars, it is usually the driver. With autonomous vehicles, this is no different, but who drives them? The answer is obviously software. This figure shows an example architecture of this kind of software, which is described in a survey paper by Payden et al. The architecture is based on multiple levels, which interact with each other, mostly in a feedback loop control style. For our approach, we decided to focus on an example with fewer layers to make it easier to explain. We interpreted these two layers as it is done in the self-adaptive community with an adaptation engine and an adaptable layer interacting in a feedback loop. In the remainder of this presentation, we will refer to the right-hand side architecture. Our aim for risk assessment will be the adaptable layer with a twofold input domain, one from the environment and one from the adaptation engine. Now I want to contrast the way in which testing for risk assessment is done for regular safety-critical systems with how we think we need to do it for self-adaptive systems. When a safety-critical system is running in an environment that is fairly well known beforehand, we are usually able to make reliable assumptions on the input space of these systems. This enables the testing of a relevant part of the input domain, reflecting system usage that we can expect after the systems are deployed. For self-adaptive systems, this is not the case. The input space has properties which do not allow for safe enough assumptions on its nature. These properties are the large size, that it is sparse, stochastic, and most importantly, non-stationary. The latter property means that design time assumptions on the input space will very likely be rendered invalid after some time. Consequently, we have to shift the risk assessment by testing from design time to runtime. I will now present an overview of our runtime approach. First, at runtime, usage data is collected from multiple instances of our system, the vehicles, at the same time. The collection takes place in a test center, which runs independent from the instances and is not interacting with the feedback loops on these systems, apart from the data collection. Second, the usage data is analyzed and an operational profile is created to form a knowledge base for the next phase. We will later see how this is done in detail. Third, tests are planned. In this state, we create a distribution of tests. Fourth, all tests are executed. If all of them pass, we can ensure the required upbound in risk. We then proceed back to the next cycle and collect data again to keep the distribution of tests up to date and with it the risk evaluation. We argue that this test selection loop allows us to ensure an upper bound in risk despite changes in the environment and the adaptation. Before I go into further detail on the process from the former slide, I first want to introduce the concept of probability of failure on demand a term that will be used often in the following slides. Let us consider a car driving around regularly. Nothing happens. It does this for a long while, but at some point in time it will be exposed to a so-called demand. Something like a rare external event. In our example, this is a tire blowout. The software of the car could now react in a correct way and steer the car to a halt, despite the fact that it has only 3 usable wheels left. Or it will fail, like collapsing to the ground and then with loss of control hit a wall. We can also attach a probability to the case of failure. This is called probability of failure on demand. Let us now consider how we actually compute risk. This formula is based on the book by Stuart Gordiner, where he approaches risk from reliability estimation. Let me unpack this formula for you. E is a single demand class as the tire blowout that we just have seen. H is the set of all demand classes. This could be a slippery road, a problem with the engine, and many more. PFD, or a probability of failure on demand, was explained in the previous slide. We compute this for each class individually, hence the subscript E, and then sum them all up to get an overall risk estimate. Attached to each demand class, there's a probability of the next demand being of a specific class E called lambda, together with the level of consequences, epsilon, if the demand is happening and the software fails. I will now give a step-by-step covering of all of these values. The aim for the end is to have all ports ready to compute the risk value, even for self-adaptive systems. The hardest or easiest part is, depending on the point of view, the lambda and epsilon values. From our perspective, it is easy because these values have to be derived from domain knowledge. This leaves us with the probability of failure on demand. But how can we get to an estimate of that before we actually see a system failing? An answer has been developed by Miller et al. In 1992 in their paper Estimating the Probability of Failure when Testing Reveals No Failures. Estimating probability of failure with testing without failures is based on a Bayesian model, more precisely the Laplace rule of succession, which is known to some people in the context of the sunrise problem. The intuitive idea is that the more passing tests we run, the lower probability of failure on demand we can assume. The formula is simply 1 over 2 plus TE, with TE the number of passing tests. We can easily see that if we had run 0 tests, the fraction becomes a half and we have a probability of failure on demand of 50%, which reflects our basic knowledge of failure when we have no prior information. If we add tests here, the probability will get lower and lower. After we replace PFD by the Laplace expression with the amount of tests that have been run and passed, we have TE as an unknown value instead of PFD. The next task is to select values from the individual TE and on top consider the context for a test for a demand class. The demand class alone does not define what exactly is tested with the TE. We need additional information about the testing context. In our example, we would like to know with which velocities we should test the demand classes, or what kind of road is the car driving on during this demand. If you are aware of the test input domain, we face the challenge on deciding on the subdomains of input to select from for testing and with what frequencies, like 10 tests with high velocity, 5 with narrow curves, 15 with wide ones, and so forth. A straightforward approach would be the uniform sampling of these subdomains. But this is a bad idea, especially with the properties of self-adaptive systems in mind. We propose to refine the selection on subdomains by an operational profile, which will be updated dynamically. An operational profile is defined as follows: a quantitative characterization of how the software will be used. This is a concept from reliability testing. Each subdomain of the input domain gets a probability assigned. Subdomains with more likely scenarios, like 50 km per hour driving, will have a higher probability. Less likely ones, a smaller one, driving with 330 km per hour, for example. The operational profile is therefore a discrete probability distribution over all subdomains. This mitigates the challenging properties of the input space of self-adaptive systems. It narrows down the input space to make it less sparse. The profile will give a distinct probability for each subdomain, thus providing a bound for each. And finally, if we evolve the profile over time, it will also reflect the non-stationary property. The limitation here is that we have to assume the independence of any demand event and events from the operational distribution. On the one hand, we have now a better understanding on what tests to select, but in general, we made the problem more complex by introducing the additional sum that reflects all the individual probabilities from the operational profile. The next question is, how do we obtain the probability distribution of the operational profile, and then how many tests for which subdomain should we spend? Let us have a look at our example and find out where the operational distribution will be collected. The operational profile in our scenario has two parts. The environment, with information like the road's trajectories in the vicinity of the car's position, its velocity and orientation, and the adaptation layer with planning horizons. But how do we collect this data? How do we collect it efficiently? We could collect data from each car and then form a profile for each. This has the huge disadvantage of an extremely slow provision of data, and as a result, a low accuracy in the profile over a long time. It might not even converge in time before the operational profile has changed again. Instead, we collect data from all running vehicles at the same time. This makes sense because they are all instances of the same system. They're just running in slightly different environments. The provisioning of data will be very quick, resulting in a dense profile. This will give us a higher accuracy in the profile. After we covered epsilon, the level of consequences, lambda, the demand class likelihood, and the probability distribution of the operational profile, the remaining open terms are the risk, the distribution of tests, and the total amount of tests. Since we want to know the distribution of tests, we can consider our equation as an optimization problem. Either we fix the risk as an upper bound and minimize the amount of tests, or we have a fixed amount of tests and minimize the resulting risk. In our dynamic context, the optimization problems formulated in the former slide will provide a basis for different strategies for an update of a distribution of tests as outlined in the beginning in the overview. With the first strategy S1, risk is computed with the current distribution of tests after the profile has been updated by monitoring. The computed result in risk compared against an upper bound, and we check whether we can ensure that. If this is the case, the process will continue to monitor the next set of data. If not, we employ the first optimization M1 and allocate additional tests, which will again ensure the upper bound. The newly allocated tests need to be run in the simulation in the test center in order to ultimately ensure the upper bound after all tests have passed. If any test fails, actions have to be taken to eliminate the failing test. This is not part of our approach though, we only consider cases when all newly assigned tests pass. The second strategy, S2, will allocate a fixed amount of tests after each monitoring cycle by application of the second optimization M2. With the optimal distribution of tests, risk is minimized for the available resources in additional tests per cycle, but we do not get an upper bound in risk. Our third strategy, S3, can be considered a combination of S1 and S2. In the same way as in S2, tests are allocated in each cycle with M2, but afterwards we make sure that the upper bound actually holds by applying M1 in case it does not, with the tests added by M2. The strategies are based on the minimization problems, but require an additional version of them. In the first cycle, the optimization problems are the ones described before. After this first cycle, we have to take existing distributions of tests into account that we already ran in former cycles. Closed form solutions to these problems are documented in the paper. I omitted them here for reasons of clarity of this presentation. Our risk estimation formula is now complete. We covered epsilon, lambda, the PIs, and finally the TIEs. But how again does this relate to the real world? And what will happen if we would not apply our approach and no more tests would be added to the initial distribution of tests when there's a change in environment? We did an evaluation to get an answer to this question. The evaluation scenario that we came up with is based on self-driving cars in a physics simulation. In the simulation environment, the cars drive between different start and target locations on a map. The maps are real-world maps that we imported into the simulation. The maps have very distinct qualities with regard to the road layout. We expected a significant change in the operational profile when we transition in deployment from one city into the other. We chose one demand class under the consideration that a single demand class can already show what the approach provides. The demand class is the already introduced tire blowout, TB for short. We researched an upper bound for lambda for this class from literature and set epsilon to 1. This value makes sense if there is only a single demand class because we do not need to express that this is, for example, more or less severe than a broken wiper or any other demand that we did not model here. Finally, we decided for an upper bound in risk of 1 in 10,000. The selection of an upper bound is dependent on the meaning of the demand classes and the meaning of the values assigned for the level of consequences. In this slide, we gathered everything from the evaluation scenario around our formula. We have the upper bound in risk, the demand class tire blowout, the probability distribution in the environment that changes due to a change in deployment in different cities, the lambda and epsilon values, and finally, our closed form solutions will provide the distribution of tests in order to compute the probability of failure on demand. In this slide, I will show how we created a simulation of change in the operational profile. As mentioned before, we collected a large data set of the environment and adaptation engine input from a simulation of driving cars. From this pool of data, we sampled and counted occurrences of subdomains where a sampled data point belonged to. The evaluation experiment went through 3 phases. First, we exclusively sampled data from the first city, C1. Then, we increased the likelihood of sampling from the second city, as C2, and consequently decreased the sampling from the first. With an increased sampling likelihood from the second city, we introduce a change in the profile. In the third phase, the sampling stabilizes and both cities are equally likely to be sampled from. How does this affect risk? Our first evaluation result is the application of strategy S1. Let us first have a look at the light red line. Starting with the moment when we have a change in profile, we see the risk diverging from the upper bound. If we ensure the upper bound and risk by incrementally adding tests to the initial distribution of tests, we can stay below the upper bound, as shown with the blue line. At the end, we will have an increase in risk of 5% if we leave the distribution of tests unattended. The evaluation also shows what advantages and disadvantages each of the strategies have. I included the vertical red line to show when the operational profile starts to change. The first one is perfect with respect to keeping the upper bound in risk, but in a real-world scenario, it would probably not be used because the required test resources are known. The second strategy provides a known test effort. A second advantage is the constant reduction in risk, even if there is no change in the operational profile. But if the amount of additional tests per cycle is not according to the amount of change in the operational profile, it might breach the upper bound. We consider this a no-go in most real-world scenarios. The third strategy is, from our point of view, the most adequate one. We combine the advantage of always staying below the upper bound with the constant reduction in risk. The necessary test resources are still not fixed, but we expect them to be more stable because a change in the operational profile is probably not happening so fast. Let us now briefly consider the outcomes. We propose to assess the risk of self-adaptive systems at runtime instead of design time. We expect a more appropriate handling of the input domain challenges with regard to the properties of sparsity, stochasticity, and non-stationarity. It results in an adequate risk estimate even when the operational profile changes. Our evaluation showed that there is an actual difference if we only consider the design time distribution of tests versus distribution of tests created incrementally at runtime with our approach. We also showed how the collective monitoring of data improves the accuracy of an operational profile. I would also like to point out that we published the pool of data and the source code which generated the data. Finally, I want to draft our continuation on this topic, targeting 4 different directions of research. Firstly, with smarter aggregation algorithms, we would like to improve even more on the preciseness of the operational profile. The introduction of a time horizon into the past where data is considered relevant should help us to forget about data that will become irrelevant over time. Secondly, we would like to work on the prediction of the operational profile. With the presented approach, when we finish our test runs, we have to be aware of the fact that the current operational profile has already developed further. If we find some means of predicting to some degree the direction of the operational profile, we should be able to test ahead instead of testing behind. Finally, we want to address the correctness of the subdomains on which the operational profile is based on. If during runtime we measure a non-uniform distribution within subdomain, we should try to reorganize subdomains by splitting and merging in order to reach uniformly populated subdomains. We are aware that this introduces issues of comparability, which we need to address. Thank you very much for listening to our talk. Please feel free to get in contact with us if you're interested in the topic.